Eigene und dann Apparativ. So, dann jetzt.
So, good evening, all of you. So, we'll be starting this session after 2 minutes. So, let's wait for others to join. Yeah, we'll wait for 2 minutes more.
Genau, aber überall steht jetzt mal, ich weiß nicht, ob ich jetzt alles von einem.
Ja, das müsste alles sowieso zu ändern. Also das wird eine Katastrophe, das sage ich schon mal direkt. Weil eigentlich müsste alles nur, diese Frauennummer ist eigentlich nur für uns intern mittlerweile interessant. Ja? Weil damit erreichst du eigentlich, oder die Damen erreichen ja immer den Raum, egal wie da ist. Euch persönlich zu erreichen, ist ja dann nur möglich, wenn ihr tatsächlich im Client angemeldet seid. Wenn ihr zu Hause seid oder hier seid. Ihr hattet doch hier angemeldet, oder?
Ja.
So, das heißt, es würde das klingeln. Problem an der Geschichte ist, ihr müsstet dann halt immer ein Headset dran in die Kiste.
Genau, das habe ich ja nicht. Und
Ja, das ist aber ganz schön. Das ist aber ganz schön. Du machst doch hier auch Videotape. Du hast kein Headset.
So yeah, so welcome to the week 5 session of electrical measurement and electronic instruments course. So we will be discussing about the content of this week 5. So we'll be going through the assignment questions, and then we'll be solving some of the extra questions. So last time we were solving some delta and star related three phase wattmeter problems. So we'll go again through that because we didn't complete that delta connection. We'll be going through that also. So yeah, but first we will be discussing about the like questions related to your assignment, so that it can help you in solving that. So these are the previous year questions, but related to like what you have with this year also. So if we talk about the I think now it's fine. Yeah. So if we talk about the first question, so there is a bridge connection. We have this L1 R1, one coil, and we have another coil L2 R2 here. Then we have R3 and R4 resistors. So the question is saying at balance they found L1 to be this, R1 to be this, L2 and R2 to be this. So they are asking us to calculate the angular frequency of the supply. So like for any bridge type questions, we will have to go through the we'll have to just look at the balance condition of the bridge, and then we can answer like many of the questions. But okay, I just remember like okay, so I will be like telling you some of the things related to the bridge networks which can help you in finding or solving these bridge related questions. So the first thing I will be talking about the quality factor of the coils. So different coils. So I think you can so whenever you will be watching these videos, so you can note down in your notes. Then yeah. So if we talk about quality factor of coils. So in this we have different types of coils. So a resistor in series with inductor. So this is R, this is inductor. So this is a resistor. Then we have in parallel with inductor, and then we can have a resistor in series with capacitor, then the parallel combination of them like this. And if you talk about the quality factor of them, so you can remember this. For this it will be omega L by R. For this it will be R by omega L. So for third it will be omega 1 by omega RC, and for last it will be omega RC. And dissipation factor for any coil is nothing but T is equal to 1 by reciprocal of the quality factor. So So whenever you need to identify the quality factor or the dissipation factor of any bridge network, so there is a coil in that network, so based on the configuration of the coil you can identify the quality factor of that coil. So this is important. And another thing which I wanted you to know about the bridges, so in this week you learned about many bridges. So for that, so there is a small table which you can remember. So that is the parameter which that bridge calculates. So this is a summarizing table, I can say. So this is a summarizing table for different types of bridges. So we will be talking about the parameter which these bridges calculate and what is the name of that bridge, and also the application of that. So you can note down these tables, it will be useful for you, like for understanding as well as solving some questions. So if we talk about self-inductance, so if we talk about self-inductance of a bridge, that is L, then we have Maxwell bridge, we have Maxwell X. I don't know if you have covered all these bridges, but just for summarizing all the things at in one table, so I'm writing most of the bridges here. Then we have Hayes bridge. So this is like used normally for medium Q, like for calculating the quality factor of a coil which is having a range of Q between 1 and 10. So this is medium range. And Maxwell LC is also used similarly like this, medium range Q, which is again Q greater than 1 and less than 10. Then we have Hayes, that is used for high quality factor, that is Q greater than 10. Then we have Anderson bridge. So if you want me to cover any of the bridges, then just let me know. I will tell the details of that bridges. So now then we have Anderson bridge, which is for low Q, that is Q less than 1. Then we also use Owens bridge, which is used for incremental inductance, like changes in the inductance value in microhenry range. Okay. And then we have this heavy side. Now we are talking about mutual inductance as a parameter. Mutual inductance, which we called as M. So we can measure mutual inductance from these bridges also. So one is this heavy side. Heavy side is measure M. So it measures M from L. So if you will know the working, so you will know why this is from M to L you are measuring this. Then we have measures L from M. So that is Heaviside Campbell bridge. Heaviside Campbell bridge. Then we also measure capacitance. So I'll just add a paper in that. Done. Okay. So I'll be extending this table. So then we measure capacitance, that is C, which is we have Dissipation bridge. Then we have modified Dissipation. So like the configuration changes for these bridges, and so if something is like if you go through these and if you are not able to understand, then you can let me know. We can do the detailed analysis of these bridges. but it's good to know their application, like why they are used. So D-sorties is used for basically purely for capacitance measurement. Then we use modified D-sorties Groover bridge for measurement of capacitance, dissipation factor, and quality factor also. Then we have Scarin's bridge, that I think you must have heard about this. That also measures CDQ. Okay, for understanding, I will write this is dissipation factor, this is quality factor, and C is capacitance. That you know. Okay. Then we have like bridges which calculates the frequency of the supply also. That we have Wayne bridge, famous bridge, and wide. So it is used for like wide ranges of F. Okay. Then we have Wagner ground correction. So these are the name of these bridges and their configuration. So Wagner ground connection, Wagner ground connection. So this is for, so in this bridge, like there is a issue of like a node to earth capacitance, that so it is used for that, like to eliminate that effect, eliminate the node to ground capacitance. So if possible, if we have time, so I will go through this, but yeah, but for just for the sake of knowledge, and also I'm just making you know about the applications of different type of bridges. And then this is important, quality factor of coils. So we have different configuration of coils, like series RL, parallel RL, then series RC, then parallel RC. So the quality factor of their coils, of these coils, will change according to their configuration, so you can note down. And dissipation factor is simply the reciprocal of the quality factor, so that you can also achieve from the quality factor. So now after this, so we will be going towards the some of the related assignment questions which you will find this year, but these are the questions from the previous year. So yeah, so now the first question says that, so we have L1, R1, L2, R2, and we have to calculate the angular frequency of this bridge. So how we will do that? So for this, so we first of all we have, see, this coil also, we have this coil also. So but let's say like we should know the balance condition. So balance condition for any this 4 element bridge, it's simple, the ratio of the opposite arms, we equate them. So if we equate them, then we will have something like this. So it will be j omega L1, so parallel combination of these two. So I am writing that only, j omega L1 plus R1 divided by the this resistor R3. And similarly for the next side, that will be the series combination of these two plus R2 divided by R4. Okay, so if we just rearrange these things, R4 by R3, so like it's also important how you rearrange these things, because if you rearrange, like although from every rearranging you will get the right answer, but sometimes it saves you a time if you do the right rearranging. So for this, what I'm doing, like I'm bringing this R4 here, so it will be R4 by R3, and I will bring rest of the things here. So it will be j omega L2 plus R2 into j omega L1 plus R1 divided by j omega L1 R1. So if we just so we have here, like in this part we don't have any imaginary part to equate with the left hand side, with the right hand side of the equation. So if we equate the imaginary part of both left hand side and right hand side, then we have, for this, imaginary part is 0, for this imaginary part is what it is, after simplification of this equation, then we have imaginary part as j omega L2 divided by R1 plus R2 divided by j omega L1 equal to, yeah, so if we equate the LHS and RHS, then we will have this. So we can equate this to 0 because this left hand side and right hand side are like, we can equate the imaginary parts of LHS and RHS, so that will be 0. And based on that, so if you take the mod of these in these, then omega will become R1 R2 divided by L1 L2 under root. So if we just so now it's simple, so just we have to put the values and we'll get 100, around 100 radian per second. Okay, so now the next question says, so they are asking for this ratio. So R4 by R3 will be what? Simply R4 by R3 will be equal to the real part of the right hand side of this equation, RHS, and that will be, after simplification, we will get that as R2 by R1 plus L2 by L1. So this is basically when I simplified this equation. This is the main equation. If I will simplify this, then I will get this thing here. So the real part of that we can equate with the real part of the left hand side of the equation. So we'll get this. So we have R2, we have R1, L1, L2. So we simply put that and we can get the answer for this. So this is also easy. Okay. Then we have so they are asking, like, given an arbitrary set of fixed values of this, is it always to obtain a balance by adjusting only the frequency of the supply? So for to answer such type of questions, we should know how the behavior of this equation is, the main equation, how the parameters are there and how they are affecting the equation. So if we just simplify this equation, then we will get to know that it is R4 by R3 equals to j omega L2 by R1 minus R2 by omega L1 plus R2 by R1 plus L2 by L1. Okay, so this was the real part which I was just discussing just above in the previous question, and this was the imaginary part of this. So I have just simplified the main equation of this. So I have simplified the main equation. So we have the imaginary and the real part for this. Then what we can do, wait, let me, yeah. So then what we can do, so now the question is asking, it is always possible to obtain a balance by adjusting only the frequency of the supply. So if we, let's say we are just adjusting the W, so we can say, if we just so they are saying L1 L2 R1 R2 R3 and R4 are fixed given an arbitrary set of fixed values of this. So L1 is fixed, okay, L1 is fixed, okay, L2 is also fixed, R1 is also fixed, R2 is also fixed, R3 and R4 are also fixed. So now they are asking, so can we get the balance condition for this? So this is basically the balance condition. Now so L1 L2 R1 R2 R3 and R4. So they were saying that can we, so if we have these fixed values, then we can get the balance condition. So it is in a way correct and wrong also. Why? Because if we just adjust omega, so we can balance this condition and make this 0. That is fine. Okay, but so whatever, so we have omega here also and here also. So if we'll increase this, so if we'll increase omega, then this thing will increase and this thing will decrease. So somehow we can get the balance, we can balance the imaginary part of this equation. But what about the real part? So if we make this R2 R1 L1 L2 R3 R4 fixed, so I don't think we will be able to achieve the balance condition for this that. So what if like the fixed value doesn't equate to this condition? Let's say you have such numbers of these r1, r2, r3, r4, l1 and l2, so that it is not equal to the both of the sides are not equal. Then you don't have any options to change one of the parameters to get this equal to each another, like LHS equals to RHS. So what I'm trying to say, if you have at least one parameter in this, in either of this part or this part, which can be varied. So if this condition is not satisfying, then you can vary that parameter and you can make this condition to become equal or balance. So that's why this will be false. By only varying the supply frequency, we cannot get the balance condition, because we'll have to look for the real part of this equation, where at least we need one more variable so that we can vary that, and then we can achieve the balance condition for the real part of this equation. So this question will be, for the answer for this will be false. So it's like more of an intuitive and logical explanations for like the questions where they ask about like if you vary this parameter, so what will happen if you will vary this, what things can go. So just go with the, just derive the main equation, separate the real and imaginary parts, then look into the question what it is asking for. Okay, so I have one question in the extra questions also relate something related to this, we will solve that also. So now the next question, the bridge can be balanced if the supply waveform is. So they are saying sinusoidal, square, triangular, any periodic function, any half wave symmetric function. So for this type, for this question, like if we go for like other types of this equations or like other type of signals, then what will happen? We will have harmonics also in that. So how it will affect harmonics means basically it will not have only one frequency, but it will have other frequencies also. So but in case of this sinusoidal, only we'll be having one frequency. So if we have only one frequency, then we can so which can be balanced because we will be having only one frequency. But if we are dealing with more than one frequencies, then for each and every type of frequency we will be having these different equations for that, because this omega will be changing, this will be varying. So we'll have to achieve this balance condition for each and every type of frequency present in the signal. So it's best if we can get the balance condition for a supply waveform if that is pure sinusoidal, because in that case we are dealing with only one frequency. Okay, so for this answer will be A. So I think this is, if okay, then so in the fifth question they are asking for the power factor of a coil. So for this in the starting of this lecture I have given you this table, this quality factor. So this now this becomes important for different configurations. We have different quality factors for different configuration of the coils, we have different quality factors for this. So we will be using one of the equations. So now in this case all the I will say that they didn't mention which is the coil which they are measuring the parameters for. So we can have L1, this can also be the coil and this can also be the coil. So even I was also like so they might have mentioned about that, but anyway we'll calculate for both of them. So if we talk about L2 and R2, that is a parallel combination of these two resistors. This is R2, if I'm right I will just check again. Okay, that is L1 R1, sorry, L1 R1, L1 R1. Okay, and we also have a series combination of coil L1 R1. Okay, so now for this quality factor will be what, as given in this table. For parallel it will be R by omega L, that is R by omega L. For series it will be the reciprocal of that, that is omega L by R. Okay, now we have the quality factor, at least we have this thing like their expression. So now we need, so now they have given the power factor of that. So if you will see in a parallel combination, if you have the if you just recall your phasor knowledge, so how the power factor relates to the impedance of that network. So for this parallel network we have, so let's say this was the voltage, this was the voltage across this, let's say this is V, this is this phasor, and the current, there will be current I1 here, there will be a current I2 here. So this I1 current will be lagging this voltage by how much? 90-degree angle, that you all know. Okay, so basically this the volt, so it will be, so this will be omega, or we can say XL, so it lags here. Okay, or here the I1 current will be there. And what about the I2 current will be here itself, and will have drop due to resistance R. So the resultant of this, if we talk in terms of impedance, then the resultant will be what? It will be Z, that is the impedance, and that will be, you know, omega L square by omega L square plus the vector product of these two, R and omega L. But the angle that, and this is also the resultant current direction also. Okay, because yeah, the resultant current phasor will be in the direction of the resultant impedance. So this is theta, this is the power factor, that is the lag of the current, the resultant current with respect to the voltage supply, with respect to the voltage across that element. So we have this thing. So if we talk about power factor, so we have basically information of this, that is 0.25. So if we do cos inverse of 0.25, so we have this cos theta equals to 0.25. We have this knowledge. So if we do cos inverse, we can get theta. So theta, we know that theta, but how we will relate to this? So this is what, this is basically, if we talk about the tan theta of this thing, what is tan theta? That is the hypotenuse upon base. So hypotenuse is what? Omega L in terms of, if we talk about in terms of impedance triangle, this is omega L and this is R. So it will be what? So tan theta will be omega L by R. Okay, for this thing now, but the quality factor is what? R by omega L. So it will be, so the quality factor is R by omega L. So quality factor will be 1 upon tan theta. Okay, for first case, and that you can find easily by tan cos inverse of theta. So you will, so you cos inverse of power factor, sorry, power factor, so you will get the theta, this is theta. So you can get that cos inverse of this from here, you will get the theta, you can put theta here, 1 by tan theta, you will get the quality factor of this for this configuration. But what if they would have asked for this coil L1 and this is L2 and R2, for L2 and R2, for this kind of configuration we again have this we'll say phasor. So we now we'll talk about it in terms of current, because this is a series network, so we have I current flowing through it, and then the resistance, the drop across R2 will be in this phasor only. So this will be R2 drop due to R2, and the drop across this L2, so the current I will lag from L2 by 90 degree. So basically this will be omega L2, or we can say the drop across this. Okay, the resultant will be something like this, it will be theta, and this will be, so here tan theta will be omega L, again omega L by R, whatever R, so R2 L2. But in this case what will happen, quality factor is also omega L by R. So we can obtain quality factor in this case as tan of cos inverse power factor. Okay, so for this coil the quality factor will be what? Equals to tan of the theta, that is the power factor angle, so that we obtained by this. But in the first case, what is happening, the combination is, if the coil is in parallel connection, then we have reciprocal of the tan theta. Okay, so did you get this thing? So for like different configurations of coil, so for those who have just joined, I just in the starting of the lecture I gave this table, this is important. Okay, so this table talks about the quality factor of a coil. So for different configurations of the coil, we have quality factors of the coils, and dissipation factor is basically the inverse of the quality factor. Using this, so we have this question like the power factor of coil is what, the 0.25, and estimate the quality factor. So but they didn't mention about the coil, so that's why I solved for both of the coils. So one coil in this configuration is this coil, and another coil looks like this coil. Okay, we have two coils here. So if you talk about first coil, then this is a parallel combination. We have quality factor as this, and then we saw the impedance triangle of this, and we relate that to the tan theta, and it becomes reciprocal of the tan theta. But in the case of the series configuration, we have quality factor that is reciprocal of this thing, the quality factor in the parallel combination. And again we did that impedance triangle thing. We got that the quality factor here is tan of the power factor angle, so that we can obtain from here. So these are the two differences between two configuration of the coils. So based on that we can answer this, although it is little anomaly here that they haven't mentioned about the coil. But for the previous year they were asking for this type of coil, like the series one in the configuration, so you can answer based on the series type of coil if you haven't answered this. Okay, done with this, we'll move to the next question. So next question says that, so this is a high voltage capacitor. So now they have highlighted this, so that's why they are talking about this configuration. So this is a high voltage capacitor CX. Okay, so this is a scattering bits configuration, and so there is a balance at C1, C2, R2, R3 and CX. So they are asking for CX basically, so we have other values in our. So now so again just easily you can do by equating the balance condition for this bridge. So the balance condition for this bridge will be, I'll write it down for you, it will be R3. So I'm talking about this too, R3 by j omega C1. Okay, I have just rearranged some things, plus j omega c2, which is equals to rx plus 1 by j omega cx. So this is basically the series combination. We would have divided that by r3, but I have kept r3 here uh, just like it's simple maths. Yeah. So after that we have this. For this configuration we have that their parallel combination. For that we have this equation. Then basically, yeah, this, and we have, for this we have this thing j omega c1, so that you can write easily. Okay, that is not an issue. So when we will solve, so always remember, just equate the real and imaginary parts of these equations. So so if we equate the real and imaginaries, then we will have cx equals to c1. So I have written that thing just to save time. So it will be c1 r2 by r3. Just be careful about your calculations. So we know c1, we know r2, we know r3 from the equation, and we can get cx easily from this. So first question is quite simple. Okay, and then we have this rx. So they also asked us to calculate rx. So rx will be, again based on this equation, like equating real and imaginary part, we will have rx as r3 c2 by c1. Okay, so this is the thing. And now, so this is also easy. Now they're asking for to estimate the dissipation factor of the unknown capacitor. So I told you dissipation factor is simply the reciprocal of the quality factor. So D is equals to 1 by Q. But the question is, what is Q? So as I mentioned. So what is the coil net configuration first? Just see, coil configuration is a series of, it's a series thing for R and C. So what is the quality factor for R and C in series? That is 1 by omega RC. So this table is really important, okay? So it will be 1 by omega RC. Although there is a logic for this table, uh, that you can derive this also, like for each and every case, but after going through that logic, you can just remember that table. That will be useful for you. So this Q will be what? 1 by omega RC. Okay, was that only? Yeah, 1 by omega RC. This is 1 by omega RC. So we have omega, we know they have given this. R is the coil resistance. So this is basically Rx, this is Cx. So we can get the quality factor if you know the quality factor. So dissipation will be omega Rx, that is the reciprocal of quality factor. It will be this. Okay, so this will also become easy for solving. If this is fine, then we'll move towards the next question. It is saying if the supply voltage of the bridge is 2 kV, okay, at a frequency they have mentioned, then estimate the voltage across the variable controller arms at balance. So variable controller arms were this one. So where they were varying the voltages like R2, C2 and even R3 also. So they're asking for which one at balance. Okay. Okay. So basically, but if we talk about, then we will be going with this because we have two parameters to vary here. So I think this is the variable controller parameters. So for this, like this, you can use any simple okay, so that they have so it can be okay. Oh, in balance condition, the okay, these okay. So but so basically, if we talk about in with respect to the R3 variable controller, then we have 2 kV R3, simple that voltage divider thing. If you have a voltage at the source and if we have two resistors or two impedance, then the drop across one impedance is the impedance of that across which we are seeing the drop, divided by the resistance of that branch, 3 plus Rx plus 1 by j omega Cx. Okay, and we will get this. So we know R3, we know all the parameters value. So basically we have to go for the mod of this. So this will be like square of this and the square of this, and the then we have the under root of that at the denominator. So this is the modulus of this. So we'll have that. So yeah, but I was thinking why we didn't went for this voltage. Maybe they say this has variable controller, but okay, I will correct you that thing for that. Okay, I will correct that in the next class. Why they didn't go for the this branch? Maybe there is a terminology like we, for this particular terminology we meant we only talk about this arm. So maybe that is the case. I'll just correct that thing in the next class. Okay. Okay, but anyway, so this is with the but the fundamental thing to remember is like which coil we are talking about. If that is the coil, then the quality factor of that coil, how you will get that, and before that, the balance equation of that bridge, and you should rightly organize the real and imaginary parts on each side of the equation. So if you have done that, you can answer these type of questions easily. So then we have one, I think this is, yeah, for this. So this question says that at balance the D factor of C4 and R4 is, so they are talking about the D factor of this coil. Estimate the Q factor of and they are asking for Q factor of this coil. Again, it will become very easy if you know that table. So the dissipation is 1 by Q. So if we talk about the Q quality factor of this, that is 1 by omega for series R4C4. Okay, 1 by omega R4C4, and dissipation will be omega R4C4. So this we have one relation. Then for this configuration, the quality factor is omega L by R2. Just yeah, omega L2 by R2. Okay, this is the quality factor, and they are asking for the quality factor of this only. So now, since they haven't mentioned the each and every value, so we will go for the balance condition. So if you will go for the balance condition, so in balance condition we can balance out the phase angles of each and every side also. So in this case, if we do that, then if we talk about the angles of all these four branches, then we have the reciprocal of R1, the angle of R1 divided by the angle of this configuration L2 and R2, which will be equal to angle of C4 and R4 divided by the angle of R3. So these two have zero angle, so that is fine. So but if we talk about this and this, so this will be what? Tan inverse of, so since this is in denominator, if we just do the uh, complex math here, so it will be minus of tan inverse omega L2 by R2, and this will be tan inverse of minus 1 by omega C4 R4. So if we equate both of this is 1 only at numerator. So I think you got this now, how we got the angle of that. So angle is basically, so I'll just make things clear for you. So we had this thing, okay, we have series connection. So the impedance of this will be what? R4 plus 1 by j omega C4. Okay, so what will be the angle for this? It will be the imaginary part divided by the real part. That is the tan of this equation, basically the argument of this equation. So this will be what? 1 by omega C4, and yeah, R4. Okay, so but this is only valid when this is in its standard form. So this its standard form is R4 when j is above the j is in the numerator, that is a plus jb. So in that form we can say it's the imaginary by the real. So here if we go for j, if we take j over like in the numerator, then it will be minus j omega c4. So for this the argument will be that omega c4 divided by this r4 but with a minus sign. Okay, so that's what I wrote here, minus 1 upon omega c4 r4, and this is, or this minus came because we carried this thing from denominator to the numerator. So if you will equate this, then we will get omega L2 R2 equals to 1 by omega C4 R4. Okay, so now we have, so dissipation factor value, this is given in the question 0.24. We have this value, so if we have 0.24, so we have this value, so we can get the value of this, which is basically the quality factor of this coil L2R2. Okay, so this will be 1 upon 0.24. You will get the answer for this. So any doubts in this? Any assignment questions till now? If no, then we will go to the extra questions for today's sessions. So yeah, just go through that what I just told you. So if you have any doubts, just let me know. Then if not, then we will move towards the next part, extra questions for this session. Okay, so yeah, so you can post that in the discussion forum also if you find any difficulties in this. So yeah, so in the last class, if you see the last class session, so there, like, we were discussing about the three-phase wattmeter and their connections and how we measure power using two wattmeters in a three-phase network. So we talked about this star configuration. So we had this W1, we had this W2. So we calculated the power of this whole system. So if we just simply uh, just wait. So yeah, if we simply say what is W1, if we just add the powers indicated in this W1 and W2 for a star, yeah, so then we will get the three-phase power of this whole thing. That will be root 3 VL IL cos phi. Phi is the power factor, the load factor, which is in the each branch. Okay, so this will be the total power. If we talk about W1 minus W2, we got this, like, we talk about root 3 of W1 minus W2. So this is all in the derivation, you can see that. So it will be root 3 VL IL sin phi. Okay, and this is the this is the reactive power of the whole system. Reactive, this is active, and based on that we formulated one, like, formula, which is the power factor of any such system can be easily calculated using this ratio. Root 3 W1 is W2, W1 plus W2, and this was for lag load. For lead, it was, there will be one minus sign here. It will be W1 plus W2, and this will be tan phi. Okay, so for this particular type of connection. So if you change this connection to, let's say, Y, then these things can also just lag and lead will become lead and lag. That will be the only difference, but this main equation, the basic equation will remain same. So this was for the star. Then we were solving for the delta. So but there was some confusion, so today I will be solving for this delta. So the question was, calculate the power factor of a balanced three-phase inductive load. So we have inductive load, three-phase balanced, and readings are mentioned. W1 and W2 are 6 and 4. So this wattmeter is showing 6 watt, and this wattmeter is showing 4 watt, 6 watt and 4 watt. So now we have to, like, formulate some such thing so that we can uh, get to the power, like, so we can get the power factor of this whole system. So what, again, we will go with that basic thing. So we have this, so we have W1, we have W2 also. We have two wattmeters, W1 and W2, which are measuring. So I again and again I emphasize on this, that you should know what is the voltage of the power coil in a wattmeter, that power coil of a wattmeter, and the current to the current coil. If you know the information about these two parameters and the angle between them, then your question is solved. So in case of W1, you have this thing. So you have this power of this W1 can be, so for W1, what is the voltmeter? So just for the simplicity of my simplicity, I will just rename this as R, this B and Y. Okay, RBY, this will be R, this will be Y, this will be B, so this will be VBR, basically this phase voltage. This will be VRY, this will be VYB. Okay, then this will be, line current will be IR, this will be IR to Y. This current is going from R to Y, so it will be IRY. This will be IYB, and this will be IBR. Okay, just name changing. And this will be, basically this current will be IB, and the current through this will be IY. Okay, because it's coming from this phase. So in delta, we have to keep this thing in mind, that the line voltages are same. So in this case, here, where should I mention? So here I mention line voltages. In delta, it is equals to V line equals to V phase voltage, that is phase voltage. that you can easily say also, because line voltage is not V, what it is VRB, let's say for one phase. So it is VRB, that is the line to line voltage. But at the same time, what is the phase voltage for this? That is also VRB. So that are same for these delta connection. But the line currents are different from the phase currents in delta configuration, because this is the line current which is flowing from this R line, the R phase line. But when it is going into the phase, then it is IR by, so it is a vector sum of like two currents. So that's why the line currents are not same. Line currents are not equal to phase currents in case of delta. So now we'll be solving the question. So so again, that power across this W1 wattmeter, it will be what, the voltage across this power coil, that will be VR. So one connection is at R and another is at B, so it will be VRB into the current of that current coil. So the current of the current coil is this, that is IR. It will be R, and the angle between this VRB and IR. Okay, one equation we got. The another, we will say P1, this will be P2 for the second wattmeter, that is this wattmeter. What it will be, it will be the power, that is the power across this power coil, that is the voltage across this power coil, that is what, this VY voltage and the B voltage. So it will be VYB, and the current, so the current coil is I by. Okay, and we have the angle between this, that is VYB and IY. So this is the angle which we have to calculate. So if we look into the phasor of the delta, so that can be given as in star, we talk in terms of voltage. In this we will talk in terms of current. So this is basically IRY. Okay, then we have IYB. So IRY is this current, then we have IYB, and then we have this IBR. This is IBR current. Okay, so now if we talk about the first wattmeter, so where this VRB and IR will be lying. So for IR, so what is IR? IR is this current. Okay, if we just use simply the nodal equation at here R node, then we will get IR as IR by, because this is this current minus this current. Okay, minus IBR. Similarly, if we talk about IY, that is the current entering through this, it will be IY will be equal to IYB minus IRY. That is the current entering into this branch and the current entering into this node, leaving from this branch, and the current, simply like you have to use the KCL, the nodal equations here, then you will get these thing. So you know this, then how IR you can get. So we know IR direction, that is IR here. IBR will be minus of IBR, so it will be less. We will go for the negative direction. So this is minus IBR, and if we add both of them, then we will get IR. So this will be IR. So this will be having 30 degree from this. Now we got IR, but where will be VRB? So VRB is at this is at this branch. At BR branch, it is the voltage drop. So that is basically the, and we know that the load is inductive also. So that means there will be some lag between the node, between this branch current and the voltage drop across that branch. So we are talking about the BR branch. So for the clarity, just look, this is the BR branch. We have some lag load here, so the current flowing through this is IBR. Okay, so now the voltage drop across this is VBR. So if we simply see the phasor of this, what it will be, we have some current IBR, but since the load is lagging, that is mentioned in the question, inductive load, that means lagging load. So what will happen? So it is the load is lagging, means the current is lagging, that means some VBR will be here somewhere. Okay, so this will be theta, so the current is lagging in this thing. So similarly, we can, in this we can make that arrangement here something like this. and this will be what V. So since the load is lagging, so we have this IBR current, so the voltage we should mention here as leading, so leading with respect to current, so that means it is lagging in respect of the current is lagging with respect to the voltage across that branch. So this is basically VBR. Okay, and we have, this is the phi angle. Okay, this is the phi angle, and so but what we actually needed, we needed the angle between VRB and IR, so it will be VRB and IR, so the angle will be, so this was so this whole thing is 30, so this will be 30 minus phi. Okay, so similarly for VYB, since the load is lagging, so VYB will be somewhere here, but first we'll calculate the IY. So IY will be IYB minus IRY. So IRY will be somewhere here minus IRY, and the resultant will be here, that is IY, sorry, and we will be having VYB here. Similarly we did with this, like for this case, and this will be what? This will be phi again, and this will be 30. So this will whole thing will be 30 plus phi. Okay, so what power we got for P1? So P1 will be VB, P1 is VRB into IR. Okay, VRB into IR into cos of this angle. So cos will be what? 30 minus phi. So this is the angle 30 minus phi. Okay, by the way, this is VRB. Okay, so this is 30 minus phi, so we got 30 minus phi. Similarly, P2 is what? VYB into IY cos 30 plus phi. Okay, so this is the thing. So using this, and VYB is basically line voltage, and this IY will be what? It will be, IY is the line current, that is IL, so it will be cos 30 plus phi, and here it will be VL, that is the line voltage, and IR is the line current, that is IL cos 30 minus phi. So if we again add these two wattmeter readings and also subtract that, we will get, for subtraction we will get that again VLIL sin phi. For addition we will get root 3 VLIL cos phi. So that is simple trigonometric thing, you can do that and you can solve that thing, so that will be fine. So if we do this, so then again that tan phi here for this case will be what? Root 3 W minus, so if we multiply root 3 with this, so it will be 3-phase reactive power again divided by the active power, that is only W1 plus W2, that is this thing. So we will get the power factor of this thing, of the whole network in delta also. So this is for lag. Similarly for lead, it will be root 3, but minus sign will be there, divided by W1 plus W2. Okay, so this will be for lead. So this is same as we got it for the star connection. This is lag, this is lead. Okay, so this was about the star connections and delta connections, or we in generalized way we can say the three-phase connections. And yeah, so you can expect some questions, I don't know, from three-phase also, but the ultimate thing is like you should know the what this power coil and current coil of a wattmeter is measuring in any kind of network, and what is the angle between that power coil and the voltage across the power coil and the current in the current coil. If you know that, so you will be able to solve that question. So so just based on this, so we will be solving this question. It's a very nice question, so just read it. So they are talking about a 2 wattmeter method employed in the measurement of power flowing in a 3-phase 3-wire balanced load system. So as we did, so there is a 3-phase 3-wire system, and they are like talking about 2 wattmeter method. So here also we use 2 wattmeters only, one was this, one was this. and wattmeter 1 W1 reads 3500. Okay, I will write here. So W1 reads 3500 watt, W2 reads minus 700 watt. Okay, if the circuit is operating at, so now the supply voltage, so whenever they are talking about three phase and they haven't mentioned about the voltage which is being mentioned in the question, so then that means they are talking about the line voltage, but that is RMS. Okay, so this is 440 volt is V line, but RMS, root mean square value. And they have given the frequency of the entire power measured. So now they are asking, like, initially there was one setup where W1 and W2 was there in this three-phase system, and then what happened, like, so they have to, like, so there was some readings here in W1 and W2 which you can see here. But now what they are asking, so they are asking, like, they want to change this configuration so that all the readings should come at W1, so W2 should show what, 0. Okay, so this they are saying. So, and they did this, how they did this, so they did this by using a capacitance in the load. So there, let's say there was a star connection, we had some load system, we had that load in this, and this power was being measured by one W1 wattmeter, and this power was being measured by W2, as we saw earlier also. So there was some drop, so there was some readings here, there was some readings here, there was some load here. But now what happened, so configuration is same, but they introduce a capacitor here in each branch, a capacitor. So yeah, so in each branch they introduce a capacitor. So what this capacitor did this capacitor actually made this W2 value 0, and all the value is being shown at W1. So this is the change because of the capacitor. So now they are asking, so what will be this capacitance value for this thing? So first, it is important to know, like, what happened in this thing, then we can answer what we have to do. So again, if you read the question, so 2 wattmeter method was employed, and the power flowing in that three phase, this whole system, it was measured using these W1 and W2. So W1 showed 3500 watt and W2 showed minus 700 watt. Now they are saying, if the circuit is operating at this voltage, and if the entire power is was measured to be appeared on W1, so now they said the entire power is now only being shown here W1, and this W2 shows 0. So how they did this by using a capacitance, introducing a capacitance into each phase. So each phase they introduce a capacitor, and they did this thing. So now we have to calculate how, what will be the value of the capacitance. So if you get the logic of this, or if you understand the question, then answering is also easy. So we'll go step by step. So first of all, so these are the wattmeter readings. Okay, so intuitively we will think, okay, what is happening actually. So see, this is, first of all, this is negative in this case. This is quite strange. So but if we recall that equations which just we got here, that is this thing. Okay, 30 minus 5, 30 plus 5 also, that is for delta, and even for star also we got this cos phi, 30. Yeah, so this is, but individual readings are, so individual readings are what, it is basically directly proportional to cos 30 plus phi. You can see the previous lectures, the last week session, it was 30 plus 5. So these are basically directly proportional to this two. So now in this case we have W1 as 35 and W2 as minus 700 watt. So W1 reading is directly proportional to what, 30 minus 5. Okay, and W2 reading is directly proportional to 30 plus 5. So what happened, like, definitely this 30 plus 5 would have been greater than 90 degree. Why? Because if this angle is greater than 90 degree, then cos 30 plus 5 will be, the cos 30 plus 5 will be negative in value, because if we are moving towards the second quadrant of that angles. So if this 30 plus 5 was greater than 90 degree, that in that case only, because the other parts of this are what? VL, IL cos 30 plus 5. This is the complete equation of W2, which we get from the derivations. So VL and IL cannot be negative. Only the thing which can be negative is this thing. So if this angle is greater than 90 degree, that means the power is negative. That's why this wattmeter showed a negative power, negative here. So that one thing. So that means that 30 plus 5 was greater than 90 degree. That means 5 is greater than 60 degree. One intuitive thing which we deducted from this this reading, negative reading, is that the power factor of the load, so this is basically the power factor of the load, that is greater than 60 degree. And we can also say that the load is lag, because it's the phi is 60 degrees, so it's much, the current will be lagging by 60, at least 60 degree from the voltage. So that means load is lag also, load is lagging in nature. But we don't know what exactly this phi is. But then what happened, but then we introduce, so we have, let's say, so this value we can say this was phi. Then what we did, phi prime, so we introduce a capacitor here in each of the loads, and that capacitor made this system less lagging in nature. Less lagging means so initially there was some angle between the voltage and the current, that was phi, this phi, okay, and that is definitely greater than 60 degree. Then we added some capacitor here, it made this angle phi to phi prime, that is, or in other way, if you want to quantify this phi prime, what will be phi prime? So they are saying that in the question they are saying, if the circuit is operating and the entire power was to be appeared on W1, that means the power of the W2 wattmeter is 0. Okay, so that means this thing becomes 0 when we introduce a capacitor. That means cos 30 plus phi will be 0 after introducing the capacitor I am talking about. So that means phi, or we can say this is phi prime now. So this phi prime will be what? 30 plus phi, that can only be happen when this is 90. So phi prime will be what? 60 degree. So what this capacitor did, so initially this was the phi, the initial angle, power factor angle was greater than 60. After introducing this capacitor, it made this power factor angle reduce the power factor angle, that is phi prime, and it made it to 60 degree. So we had a large lag between the current and the voltage. Now what, by introducing the capacitor, this got reduced and this becomes 60 degree. Okay, so this is also, you can also, so why we did this, if we talk about the industrial industrial thought process, what they thought. So they thought, like, in this case we will get more reactive power in our system, but actual power what we need is active power. So that's why, in order to decrease the load, decrease the power factor, we had to introduce the capacitor. So that's why in this case the active power will increase, reactive power will decrease. Maybe this may be the thought process of the industrialists, which they thought, and that's why they introduced a capacitor to reduce the power factor to 60 degree. So now this intuitive understanding, now we build this intuitive understanding. Now the next step, so now we have to actually identify what is the value of the capacitor. Now so what you can do, so you know this formula, that is root 3 W1 minus W2 root 3 W1 plus W2. So if we talk about initially, that means without capacitor, so we will calculate the power factor. So we have this formula now, you know this formula that we have derived already. So the power factor will, so W1 W2 we know that will be root 3, sorry, this will be not root 3 here, so it will be 20. So we had 3500 minus, so don't mess with the signs, whatever sign we have we will put that as it is, 3500 plus 700. Sorry, this will be minus because we have minus sign, and this will be minus 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 minus. Okay, so we will get after calculating, we will get phi as this. This is the old phi. This is the old power factor. That will be 68.94 degree. So see what this capacitor did. It made this 68.94 to 60 degree. That means 8.94 degree angle it reduced in the power factor. Okay, so this is why they introduced the capacitor in this. I'll add one page in this. So so we got, okay, what was the initial power factor? They reduced to 60 degree, but now we need to know what will be the value of the capacitance. So if we say what is the power consumed in each phase, that is what, so the total power, total three phase power is what? It is actually W1 plus W2. Okay, and that we can get as 3500 minus 7, so plus of this minus 700, and that will be what, 2800 watts. So this is total power being consumed by this three phase network. Now what will be the power in each phase? Power in each phase, it will be the total power, that is W1 plus W2 divided by 3. Simple, because each is balanced, the load is balanced, and it is mentioned in the question also, the balanced load system. Okay, so that's why we can simply divide it by 3. So each phase is contributing equal amount of power in the total power equation. So we can simply do 2800 by 3, that then we will get this as 933.33 watts. Now so now from the three phase system we went into a phase, because we want to calculate the capacitance value. So after getting this, what will be the what this power means? This is the V phase, the voltage drop across that phase, into the I phase, the phase of the system, and the power factor of that individual phase system. So now we know what V phase will be. Since this is a star connection, we can say this is V. This in star connection, the line voltage is not equal to the phase voltage, so we can say this is VL by root 3. Okay, I phase and IL are same, so we can, but anyway we can keep it as it is, cos phi. So this we have. Now what will be the this phase angle? This phase is what? This is phi. So this is basically phi prime after adding the capacitance in that. So phi prime is what? 60 degree. So we know VL is what? 440 by root 3. We don't know I phase current. We have this is that is half, and we know this power. So based on this we can calculate I phase as, it will be 10.26 ampere. So this we got, so this is the phase current in each and every phase of this system after introducing the capacitance. Now using this value, what we will do, I'll add one more page. Add. Okay, so now I phase we know. So there was a branch, so just to, we added one capacitor, so I'm just talking about one branch. So the I phase in that branch is what, 10.26 ampere, and V phase voltage was 440, the line voltage divided by the root 3, that is basic thing. And then we have this thing, yeah, so we calculate the I phase. So can we calculate the Z of this? So Z will be what? It will be V phase by I phase, the impedance of that phase. So it will be, V phase will be what? V phase is 440 by root 3 divided by 10.26. We will get 24.76 ohm as the resistance. Now if you know the Z phase, this is the phase impedance, Z phase. So the R phase of this will be what? Z phase into cos phi. Okay, so this Z phase into cos phi will be 8.86, simply cos phi prime basically. So this is 60 degree, we know that Z phase we just calculated, and this will be 8.86. So we know Z phase also equal to X phase square plus R phase square, that is the real and the imaginary part. So using this we can get X phase as what, 23.12 ohm. So this is the reactive part of the system when we introduce the capacitance. Now so for when capacitance is there, in case of capacitance, without capacitance, if we compare these two, they are tan phi prime, tan phi. If we talk about their impedance angle, so this will be X phase by R, and this will be X phase in case this, let's say, X phase by R. So the resistance part, the real part of the system remains same. We are only adding the capacitance that will hinder the reactive part of that system. So we have this equation, and X phase, yeah. So this will be what, 10. Okay. So this will be tan 60 degree because we added capacitance, and this will be tan of 68.94. Okay, this is the old value of the power factor, and this is the new value of the power factor. So using, and what is the new value of this X phase? That will be, okay, so this R we know, okay, we know this 1060. Okay, so what we did, we can divide these two equations. So we will get tan 60 or tan 68.94 divided by tan 60, which is equals to this X phase divided by X phase prime. We have X phase prime as so basically this is the new, because after adding that capacitance we have this X phase prime, that is 23.12. Old X phase we don't know, and this 68.94 will be 2.598 something, this will be 1.73. so if we calculate, we will get X phase as 15.413. so this is the old value of the reactance part of the each phase. So if we just do X phase prime minus X phase, it will be what, it will be 7.707 ohm. So what we understood, so this is the value when the capacitance was added, and this is the value when without the capacitance in the question. So we got this much of difference, so that means this much of difference is due to the capacitance. Okay, so we can say this is the reactive part because of the capacitance Xc, which is 1 by omega c, which is equals to 7.707. so what will be the capacitance value from this equation? It will be 1 by omega into 7.707, and it will be 0.41 millifarad. So this is the value of capacitance. So what was the question? Question was, we use 2 wattmeter in our system to measure 3-phase power, and we use only 2 wattmeters. So initially the power across each wattmeter, that W1 and W2, it was 3500 watt and minus 700 watt. Then we introduce a capacitor in each load, in each phase, and then the power, W1 power, so all the power that was was initially it was there, that is total power. So now it appeared only in W1 wattmeter, so the W2 wattmeter power becomes 0. Then they were asking then what was the capacitance value which made this thing to happen? That means the W2 power became 0 and W1 was reflecting all the three-phase system power. So we solved that. So you can go through this. Okay. Yeah. So we'll move towards the next question. So just read it. So this is basically, there is no reactive part in this load. So in this figure, so there is a three-phase delta connected load supplied from a 400 volt. So there is a 400 volt supply, and we have this pressure coil of this wattmeter. So only one wattmeter is used here, and current coil here there of wattmeter are connected to the load as shown. Okay, with the coil polarities suitably selected to ensure a positive deflection. Okay, the wattmeter reading will be. So they are asking for this wattmeter reading. So as I always tell you, like just remember the volt. Just that you should know what is the voltage across the power coil, the current from the current coil, and the angle between both of them. So if we talk about in that manner, so the power will be the voltage across power coil current, and then the angle between VPC and ICC. Okay. So VPC is what in this case? It is VBC. Okay, so this is one node and this is another node, that will be VBC, and also we have ICC is what? IAC. This current, that is the current coil current, and the angle between them, let's say it is theta, some value. So VBC is what? This is the phase voltage, that is 400 volts, and in delta the phase. So 400 volts basically is the line voltage, but in delta, line and phase are same volt. They have same voltages, line and phase. So this VBC will be 400 volts. Okay, one thing. And what is IAC? IAC is the phase current, and that we don't know. So that we also know, basically it is 400. So I phase. So what is the voltage across this? That is 400 across this branch, 400 volt. And what is the impedance of that branch? That is 100. Okay, so we got that I phase as 400 by 100. So now, but the issue is what the angle between them. So that is important. So if we draw the phasor of this, again we can do this. So this is IAC, this voltage, this branch current, then this branch, and then I will go for this branch, IAC, ICB, like this and like this. So and then IBA. Okay, so this is the in delta configuration, the current in phasor form. So these all are like 60 degree apart from each other. So this is IAC. Now we need the angle between VBC and IAC. So we know IAC is here, and where will be VBC? So VBC is this one. So if we say VBC is the voltage up across this whole of the branch, but in a phasor manner. So VBC will be what? VBC will be VCA, that is the drop across this branch, then the drop across this branch, VCA plus VAB. Okay, so this is the drop of VBC. So now VCA and VAB we know. So VCA we know the phasor of that at least. So these Z1 and Z2 both are resistive in nature. So the voltage drop across that will be also in that same phase. So VAC is here. So if you talk about VCA, that will be, this will be minus IAC, and VCA will be in this it will be 180 degree apart from the IAC, because we are talking about VCA. Okay, VAB will be what? It will be, since this is BA, it will be VAB will be here, VAB. So this is VAB, that is apart from this. So now we know why. Now we need VBC. So VBC is basically the phasor of both of this. So the phasor of these two, if we calculate, it will be this VBC. Okay, so it is the phasor of these two, VCA and VAB. So now we know VBC is what, and so now we can get the angle between VBC and IAC, that is what, 60 degree. This will be 60 degree because this all will be 120 degree, so this half will be 60 degree. Okay, this will be VBC, 60 degree. So now we know the angle between the power coil voltage and the current coil current. We can get the power of this, that will be 400 by 100 into cos of 60, so that will be half, so that it will be 16, it will be 800 watt. Okay, so this will be the answer. So you should have the understanding of vector addition, the phasors, which so that you can calculate the angle between the power coil voltage and the current coil current. Yeah, so this you should keep in mind. Now this question, just read that question. So the question is like it's saying that V of t, this V of t is having this like two frequency components in that. Okay, it's supply, and we have I of t, that is through this load, and that is this thing. So they are asking what is the average power of the wattmeter. So when we talk about the average power, so it is VI integration with respect to time divided by time. Okay, but if you, so you can check on your own. So if you just omega t, so if you have two different frequency components, sine omega t and cos, let's say it will be sine omega 2t, so the average of them over a time period, it will be always zero. It will lead to, for if you are averaging a periodic, so this is basically a periodic signal. So if you are averaging a periodic signal, the average will be zero for that, because just if you see simple sine wave, so if we talk about the average, then it will be zero also. So similarly, if we do product of these two, so basically what will happen, this will be what, sine omega 1 plus omega 2 t sum by 2 something, and I don't know exactly, it will be cos minus cos of omega 1 minus omega 2 by t by 2. So this is also a periodic, this is also periodic, so this will be zero, the average of these signals will be zero. So only, so what will happen here, so we have v of t as e1 sine omega t, we have e3 sine 3 omega t, and we have I of t, I1 sine omega t minus 5 plus I3 sine 3 omega t minus 5 3 plus I5 sine 5 omega t. Okay, either you can go directly with this formula, or if to avoid the like that formula and you have to save the time, then what you can do, you can see, okay, this omega is one frequency component. If it will be multiplied with the different frequency component, then it will be zero. Okay, I will add one page and clearly tell you this. And Yeah. So, oh, okay, it was added there. Sorry for that. Let's give Yeah. Now, so what happens like if the frequency component is same, let's say if we are multiplying sine omega t with something sine omega t minus phi. So what will happen if we'll just multiply them? Then it will be cos of omega t plus omega t minus phi by 2 something minus cos of omega t minus omega t plus phi by 2. So this frequency components get cancelled, so this is basically a DC component, this, but this will be having some 2 omega t plus minus phi by 2. So this is basically periodic, and this we have as a DC component. This is DC, this is periodic. So I'm saying when we multiply two signals with same frequency, what happens? So now when we talk about the power average power, so we will have to average this out. So if we go for averaging with respect to time, then every time all the periodic signals become zero, because if we average them over a time period, so on this time period is basically the multiple of this 2 omega, this time period of this signal, so this will become zero, like all the time. Only thing will be left is the DC part of that. So for this reason, using this concept, so if we just multiply omega with the same quantity, then only we will be left with the DC component. That will be E1 I1, that is E1, and this is I1 divided by 2 sine of phi, sorry, cos of phi. We'll have cos here, okay, cos of phi. Oh, it is all this clearly I will write cos of phi. Similarly, if we multiply omega this term with 3 omega t, then since the frequencies are not same, so the ultimate result will be 0 if we average that out. And similarly, omega t with 5 omega t will also not make any sense. If we talk about this component, multiply with this first component, then again it will be 0 because we have 3 omega t and omega t as a component. But if we multiply this component with its similar frequency component, that is sine 3 I3 sine 3 omega t minus phi 3 phi 3 no phi phi yeah phi 3, then it will be again E3 I3 by 2 cos of phi 3. Okay, so we will get this thing here, and again we don't have any 5 omega t component in the voltage, so we will not receive 5 omega t as a power output, like the component, because of power because of this component will not get at the power of this wattmeter, based on this concept which I told you. So the ultimate power will be this, the average power. So it is the third option, yeah, E1 I1 cos phi 1 E3 I3, yeah, this option will be the correct answer. Okay. So if this is fine, then this question, so it's saying that in this question it's saying that there's a rotating conductor of 1 meter length. So this we have here in a radially outward direction, so the magnetic field is radially outward. So there was one axis, z axis, and the magnetic field is outside in all direction. Okay, you can just imagine this as to be 3D. So these are backward lines, and we have in front, we have like this, so it's like radially outwards from that axis. This magnetic field is there, and the magnetic flux density is given as 1 Tesla. So the conductor is parallel to the conductor is in parallel to and 1 meter distance from the, so there's a conductor which, let's say we have here, this is the conductor, and it is 1 meter distance from the xz axis. This is 1 meter, and its length is also, I think, 1 meter, yeah, 1 meter. Now the speed of the conductor in rpm required to induce a voltage of 1 volt. So when we move, so we know that famous equation, the EMF is induced if we move a conductor in a magnetic flux in a magnetic field. So that is EMF is generated, that is given by BLV sine theta. Okay, and sine theta, this theta is basically angle between the magnetic flux density and the velocity of that conductor. So this conductor is like moving, so this is axis, so it is moving like this. Okay, so basically at tangential point, if you see, the magnetic flux density is like this, like in this direction, and velocity is in this direction. So there will be a 90-degree angle every time between this conductor moving velocity and the magnetic flux density. So this theta will be 1. So B we know, L we know, V also we know, 1 1 1, and okay, V we don't know. So this will be 1, and EMF is 1 volt. So V is 1 meter per second, but they are asking for a rotation per minute. So this is basically so if we have to convert this, so what we can do, rotation per minute, that will be uh, okay, so this is for per second. So if we convert this into minute, that will be 60, and this will be divided by 2 pi, that will give rotations per minute. Okay, so this will be almost 9.549 rpm omega, we can say. Conversion from that tangential velocity into the radial velocity. So this is rotation per minute, 9.549. Okay, so if this is fine, will so there's another question with respect to the wattmeter. The question is saying that so there is a three-phase balance load. Again, we have a three-phase balance load which has a power factor of, okay, so for that load we have a power factor of cos phi equals to 0.707, is connected to a balanced supply. Okay, the supply is also balanced. The power consumed by the load is, so the load is consuming power as, oops, yeah, so the power consumed is 5 kilowatts. Okay, the power is measured by 2 wattmeter. So 2 wattmeter method is used. The readings of the 2 wattmeters are, so based on this, either this, which will be the reading. So we know that the equation √3 W minus W2 divided by W1. I have derived this already, so those of you who don't know, so they can check the last week's session also and the initial part of this session. So this will be what? This will be tan of power factor, we know 0.707. So this is basically 45 degree. So 45. Okay. So we have 1 by √3 W1 minus W2, and we also know that the power consumed by the load is 5 kilowatt. So that is the total power, we know that is 5 kilowatt. Okay. So using this, we have two equations. W1 minus, if we solve this thing, we will have W1 minus W2 equals to 2.886 watt. W1 plus W2, we already have 5 kilowatt, that is given in the question, that is total power by the load. So using this you can solve for W1 and W2. Okay, that will be this one. So it's like if you know this thing, so it becomes very easy for you to answer these kind of questions. And this is one of the gate questions, 2015. So if this is okay, then the next question. So three-phase unbalanced load, they are saying. So there is a three-phase unbalanced load. We have inductor. We have resistors here. So till now we were just looking into balanced load, but now here we have this inductor here, and then we have two resistors in these two branches, Its power is measured by two wattmeters, P1 and P2. So P1 they are saying that is a 720 watt, P2 is 580 watt. So the phase difference between V1 and I2 is, so V1 is this voltage and I2 is this current. So they are asking what will be the phase difference between these two. Okay. So how you will calculate this? So again, if you know that the knowledge of phasors, then you can easily get the answer for this, because since this is a star phase, star network, so we will have this as a phasor. So this will be what? This will be uh, VR, or that is V1. So this VRYB, so VY will be, this will be Vy and this will be Vb, and Vb I am saying this is V3, this will be V2. Okay, based on this is V2, this is V3, this is V1. Now so P1 will be what? P1 will be the V1 to 3 voltage, because it is connected a V13, and the current will be I1, and the angle between V13 and I1. Okay, and P2 will be V2 to V3 into I2. Coil current is I2 into cos of V23 and I2. Okay, this is there. Now so now when if we see in the phasors, so we need the angle between V1 is this. Okay, V1 is this voltage V1, and I2, so I2 is this current. Okay, but first of all we will, so if you know this thing, so how we will approach this? So V23 basically it is 23, it will be, if we say this is Vy, Vb, this is Vr, so this will be 23 Vyb, this will be Iy. So Vyb, so it will be Vy minus Vb, so it will be Vy will be here. Okay, and this will be 30, this will be 30, this will be V minus Vb, or minus V3. Okay, then so we need V1 is this and I2, so I2 is the current through Vy, so this is the Vy voltage drop, or we can say V2 voltage drop, and I2 will be what? I2 will be I2, so I2 is the like current through this branch, and we have this inductive load there, but there may be some resistance present in that load. So for that, like so this is the Vy voltage, so let's say I2 will be lagging this Vy voltage with some angle theta, so it will be I2, in this case I2 is this. Okay, and this will be, or it can be written as Iy also. So this is the theta angle, and we need the angle between V1 and I2, so this is the angle we need. Okay, so we already know that this angle will be, so this is basically 120, this is 120, so angle will be 120 plus theta. So this thing I told you just to like to have the understanding of phasors. how things work in phasor. And so we have, so basically, so normally the angle will be more than 120, so this cannot be there, this cannot be there, so we just uh, eliminated two options. So we can have this or we can have this. So how will we solve it? Again, we have that formula, that is root 3 w1 minus w2 w1 plus w2, which will be, so we have this value, so we can put this in this equation. We can get the answer as 130.6. so this is basically the angle between the power factor angle between sorry, this will not be 130.6, this will be 10.6 degree. Yeah, so this is the angle, this is the power factor angle, and using this we can solve this total angle, that will be 120 plus theta, which is equals to 130.6 degree. So this will be the answer. So this is the angle between V1 and I2. Okay, so then we have this question also. This question is also easy. So this question is saying that you have balanced three-phase circuit where we have C naught and line-to-line RMS voltage is 440 volts at 50 hertz. The reading of the wattmeter is, so they are asking what will be the wattmeter reading. So again, VPC coil is having a resistance voltage of VRY, that is R and Y, and we have the current coil current as IR. Okay, then line to line RMS, so RMS line to line is 440 volt, this is RMS given. So wattmeter reading will be what? VRY IR, and cos of angle between VRY and IR. Okay, so this is the thing. And VRY will be what? In a star phase connection, the line voltage, this is, so basically this is the line voltage, so it will be 440. The phase current or the line current are same in IR, so it can be so then since we know the phase impedance, so we can get the phase voltage will be V440 by root 3 divided by the impedance of that will be 1 by modulus of j omega c, okay, into the angle between these two, theta. So again for the angle, so you will have to again draw that phasor for that. So again, if we calculate the angle for this, that is VR, we have VY, we have here VB, we have, and the phase, the current angle, the current will be leading in this case, and this will be phase current or line current are same, so it will be leading by 90 degree because we have a capacitance in each of the branch. So this is 90 degree, this is VR, that is the line voltage, and so we have VRY, so VRY will be somewhere here, VRY. Okay, so VRY is this line voltage, line to line voltage, and this is the phase voltage. So the current in that phase is leading that by 90 degree, you know that, and this is 30 degree, so this was minus VY. So we need angle between VRY and IR, so this will be what? 90 minus 30, that will be 60 degree. Okay, so this will be 440 square divided by root 3 into omega c, that is like the modulus of this, into cos of 60. Okay, so we get this answer as 143.97 watt. So yeah, this is the answer for this. So so there are some other questions, but so these are based on the bridges. So we will do this in the next class. I think there's lots of things for this session. Yeah. So this will start freshly in the next session. The questions based on the RC net, the bridge network. Okay. Yeah. Meanwhile, you can also solve this as homework. So I'll mention this as homework. So you can freeze this window on your screen and then answer this. Then this is also a homework. But anyway, we'll solve this in the next class. And then this is also a homework. Okay. So this similar kind of question we solved in the assignment question also, where we were being asked to adjust one of the parameters and like to tell whether it will affect the balance condition or not. So similarly, you should also logically approach this problem, and then you can answer this question. So that's all for today. So if any doubts, otherwise we will end this session. Yeah. So yeah, if no doubts, then I will end the call. Yeah, thank you.